Hi, welcome to Unit 3.2, Thermodynamics. This is part 1 of 3. In this video, we're focusing on the first key question: what are the factors that drive a reaction in one direction or another? Okay, so as we talked in the previous 3.1 video, there are two things that chemists want to know when studying or performing reactions. One is kinetics, that deals with rates. We haven't covered that yet. And the other one is thermodynamics, which tells us how far a reaction proceeds and how much energy is lost or gained. And that's what we're focusing on in this unit, is thermodynamics. Now, there are several laws of thermodynamics. These are the sort of things that you don't need to necessarily memorize per se, but it's always important to keep them in the back of your mind to know that these are the laws that sort of govern the thermodynamic processes that we'll be looking at. In the last video, we focused on zero and the first law. We're going to focus on the second law, which states that the entropy of the universe is increasing. We're not going to fully dissect what that law means, but in this video we will learn what entropy is, and we will learn about spontaneous processes and how it relates to entropy and also enthalpy. So my first question to you was, one of the things that we focus on in thermodynamics is like what drives a reaction or a physical change forward or in reverse, whichever direction that you tend to focus on. We typically focus on forward first. Okay, to begin with, you need to understand what I mean by drives a chemical or physical change. So I want us to go back to the previous unit where we looked at the dissolution or dissolving sodium chloride or silver chloride in water. These are two different salts. Sodium chloride will dissociate completely, so all of it will break apart, and silver chloride won't. So it will only dissociate partially. And you may have been asking yourself, well, why is that? Okay, so when we say what drives a chemical or physical change, that's sort of the thing that we're asking. What drives the sodium chloride dissolution to completion, and then the silver chloride to go only partially complete? So what moves those reactions to do what they do? And the thing that drives a chemical or physical change is the same thing or the same reason that a ball rolls down a hill, and that is to get to the lowest energy state or the more stable state. And you may remember this from physics. The ball at the top of the hill is at a higher height. It has a higher potential energy. As it rolls down the hill, it loses some of that potential energy to kinetic energy. And then when it stops, the kinetic energy is zero, and its potential energy is also less. So now, compared to the top of the hill, the ball at the bottom of the hill is a lower energy or more stable state. Okay, so that's the same thing that drives chemical or physical change forward, is that chemical or physical changes are going to go to a low or lowest energy state, lowest if they can get to it, or a lower state if they can't get to the lowest. And before we proceed forward with looking into that, I want to introduce a term to you, and that is this term here, spontaneous. So let's take a look at what this means. The ball will roll down a hill on its own, so that's the spontaneous process. But if you wanted to move a ball up a hill, you would have to help it up, and that's non-spontaneous. So spontaneous means is any process that proceeds on its own without any outside help. And as reactions proceed to a lower or lowest energy state, that's going to happen without any outside help. You don't need to help it to do that, in the same way you don't need to help a ball roll down a hill. That is going to depend on experimental conditions. For example, temperature and pressure are two that are very common. So if you take cookie dough and you put it in an oven, it's going to bake into cookies on its own. You don't need to do anything extra. But if you put it in a freezer, cookie dough will not bake on its own. And so that's to show you that the baking of cookie dough is spontaneous under high temperature conditions. And so again, temperature, pressure will affect whether or not a process is spontaneous. The next thing is that if the forward reaction is spontaneous, then the reverse will be non-spontaneous. This is something that's useful to keep in the back of your mind when you're studying reactions. So if you know going from reactant to product is spontaneous, you know going from product to reactant is non-spontaneous, and vice versa. The last thing I want to say to you is that this does not mean something can be spontaneous but not fast. So spontaneous does not mean fast, and we're going to see that in a moment. So let's take a look at this CFU. Which of the following processes is spontaneous. Select all that apply. Pause the video now, read through the choices, and when you press play again, the answer will be revealed. Great. So spontaneous process is one that happens on its own, and you can leave a bike outside and it will rust on its own. You don't have to do anything extra. However, if you put an ice cube in a freezer, it's not going to melt on its own. You can get it to melt by increasing the pressure on the ice cube, but it's not going to melt on its own. Finally, the last one is to highlight is that a spontaneous process is not always fast. So graphite will on its own turn into diamond. You don't have to do anything extra to it. You don't need to have high temperature, you need to have high pressure. It will happen on its own. However, it takes a long time, millions and millions of years, and that's why we never see it happen. This is to show that something can be spontaneous, but really slow. So now that we know what spontaneous is, let's come back to get into this question. So we said what drives a chemical or physical change, and essentially it's a spontaneous process that will naturally tend toward low or lower energy state. That's what's really driving it, getting towards having the process be spontaneous or not. So now, what are some ways we can get into that low energy state? There are two things that we're going to look at here: enthalpy, which again is associated with heat change, so heat either absorbed or lost, and entropy, which is disorder. So that's a new term. We're going to get into that later. But let's see if we can make some predictions first. So we know that to drive a chemical or physical reaction forward, we want to get to a low energy state. How can heat or enthalpy help us? So to get to a lower energy state, do we want to absorb heat or lose heat? Should the sign in delta H be positive or negative? Pause the video now and think about your answer. Great, so to get to a lower energy state, delta H should be negative, because remember, that will be an exothermic process, so heat or energy is exiting the system. So the system is going to become at a lower, to result in a lower energy. Entropy, on the other hand, measures disorder. So let's check that one out. What do you think will get to a lower energy state? Should we increase disorder or decrease disorder? So pause the video now, and when you press play again, all right, so for disorder, it's actually increasing disorder. If you increase disorder, you will get to a lower energy state. Entropy is not really disorder, but it's helpful to think of it that way. Let's focus on enthalpy first for the rest of this video. And we've talked about enthalpy before. We know it measures the heat content of a system. We looked at these equations to prove that the enthalpy is equal to heat at constant pressure. Now, we just talked about that enthalpy, by losing heat, it increases spontaneity because it reduces the energy in the system. So we just talked about that, and that should sort of make sense to us. Lowering the delta H will lower the heat, and that means that the energy will be of the system will be lower, so it means it becomes more spontaneous. But that does not guarantee spontaneity. So just because you have a negative delta H or you have an exothermic process doesn't mean it's spontaneous. Let's take a look at two examples. So one is burning wood. That is exothermic. Heat is exiting the system, and it's spontaneous. If you burn wood, it will go on its own, no problem. But what about ice cream melting in the sun? Is that an endo or exothermic process? It's an endothermic process, and but still it happens on its own. You don't need to help it. So it's also spontaneous. So it's endothermic and spontaneous. And so just because delta H is negative doesn't mean it's spontaneous. Okay, now I said we're focusing on enthalpy. We're also going to be focusing on the phase changes. So I want you to take a moment to predict the enthalpy change when going from a solid to liquid, liquid to a gas. And this is just sort of to set us up for the last thing that we're going to be doing, see if our understanding is clear. Great, so going from a solid to a liquid, you need to put heat in, and so the delta H should be positive. It's an endothermic process. Going to a liquid to a solid, liquid to gas, again, you need to put heat in, like to boil water, you would need to put heat in, and again, that's an endothermic process. All right, all of this is just sort of to get you prepped for thinking about what we're going to be doing finally, and I just want to note before we get into the heating curves here that phase changes can be endo or exothermic processes. So here I shown all of the arrows in red. Those are my endothermic process. So to go from a solid like ice to a liquid water, you need to put heat in, and that's endothermic. Going from a liquid to a gas, you need to put heat in, and that's again endothermic. So all the red arrows are endothermic and all the blue arrows are exothermic. If you want to pause and take a moment here to sort of just study this video, annotate the arrows to get a sense, and then we're going to move forward. Okay, the last thing I want to go over is what's called heating curves. These are important tools that are utilized in in chemistry, and you'll see more about how they're used. But first, let me tell you about what they're showing you. So take a look at the y-axis. It has temperature, and it shows temperature increasing. On the x-axis, it's showing heat being added. And so what this heating curve is showing you is what happens to, as you add this amount of heat to a system, what's going to happen to the temperature of the system. So of course, as you add heat, the temperature to increase. So that sort of makes sense. But you'll notice that there's some flat portions here where you're still adding heat, but the temperature doesn't go up. And that may be a little weird, like, well, why do we have these flat portions here? Let's first annotate this and see what's on each portion. So on these diagonals, we're going to have our phases. Solid, liquid, gas. So we start off with the solid because that's going to be at the lowest temperature, like ice will be at a lower temperature. The next one, of course, will be liquid, and then we should have gas. Now, on the flat portions, we have our phase changes. So we have going from a solid to a liquid or a liquid to a solid. And we're going to show that as an equilibrium reaction. And this is where ice would melt or freeze. So this is the melting or freezing point portion. What do you think this portion is? Yeah, that'll be a boiling or condensation portion. So liquid to a gas is boiling, gas to a liquid is condensation. And so that's what's along these curves. Now you can utilize these curves to identify the melting point and temperatures or the boiling point temperatures of a substance. So how do you think you do that? How do you think you would find the melting point, which is the temperature at which something melts, or the boiling point temperature at which something boils? Great, so to find the melting point or the freezing point, because those are the same, that would be at the same temperature, temperature something melts or freezes, you would find the portion of the curve between the solid and liquid that's flat, and then scroll over to that temperature, and the temperature that you find on the y-axis here would be the melting point or freezing point. All right, I want you to try and do that for the boiling point as well. Great, so you would find the liquid to gas, that flat portion, and that's your boiling point temperature. So a couple things I want to note here. The normal boiling point of water is 0 degrees, and freezing point is 0 degrees, and the boiling point is 100 degrees Celsius. In fact, this is why the Celsius scale is what it is because it goes from 0 to 100 using the freezing point and boiling points of water. Take a moment to annotate all this in your notes. Okay, so let's do a couple CFUs. I want you to identify the boiling point and melting point of the substance shown in the phase diagram. All right, so pause the video now. Let's see if you can read a heating curve. Great, so the boiling point here, so the boiling point occurs at the second flat portion where you go from a liquid to a gas, and that's at 60 degrees. And then the one, the melting point is the first flat portion, and that's negative 60 degrees Celsius. So again, you would just scroll over and find the temperature on the y-axis. All right. All right, sorry about that. We have one last CFU, and again, this is just seeing if you can read a heating curve, so we can apply this knowledge in the next video. So which phases is or are present at these points? So pause the video now. When you press play again, the answer will be revealed. Great, so at A, it's just a solid. B, solid and a liquid, because both of them are in equilibrium, so they're both there. C is just a liquid. D, again, liquid and gas, because it's in equilibrium. And E is just a gas. So that's what those are the phases that are there. All right, that's it for this video. We're going to move on to part 2, where we sort of apply this knowledge in a different way. Pause the video now, and we'll see you later.